Okay, thanks everybody, and thanks for your patience as we went through minor technical delays here. Okay, so we have two talks today that are kind of rehearsals for the FPGA conference in a week and a half. And we'll start with Henry Wong and work with Vaughn Betts and Jonathan, comparing FPGA versus custom CMOS and the impact on processor architecture.
Thanks, Paul. Okay, so suppose I want to design a microarchitecture for a processor. What I have will be a set of circuits that I will somehow arrange to make a processor. And which circuits I decide to use and how I arrange them will depend on how efficient those circuits are. And that in turn depends on which substrate those circuits are actually built on. Traditionally, high-performance processors have used the custom CMOS substrate, but since we're here, our focus is on the FPGA substrate. So, to make good microarchitecture choices, we could use existing processor architecture research. However, that research usually assumes a custom CMOS substrate, and we do have to adapt it for the FPGA substrate if we're building FPGA processors. There are existing comparisons of overall delay and area between these substrates. But we do need more detailed comparisons at the building block level in order to actually influence microarchitecture choices. So this work provides this comparison of a set of building block circuits, and then we use the results from these comparisons to infer how the microarchitecture of processors might change when you want to build a soft processor instead of a hard processor. So in this work, we have basically three parts. The first, we're going to measure the overall delay and area of processor cores, a complete circuit. The second part, we're going to compare a very similar comparison, except we're going to do this for small building block circuits that usually go in processors. And then the third part, we use the results of the second part to infer how microarchitecture might change. Methodology. In most cases, the FPGA circuits were synthesized through Quartus. We used the largest and fastest speed grade of the Stratix 3 FPGA. And the FPGA areas were calculated using resource usage and FPGA tile areas provided by Altera. A few of our results are cited from literature. For the custom CMOS side, all of our design examples are from literature because we don't have the expertise to do high-performance circuit design and layout. And because it's from literature, they're not always from 65 nanometers. So we normalize everything to 65 nanometers to do comparison. We assume ideal area scaling, and we assume ring oscillator delay scaling, both of which are optimistic, but since we're only limiting ourselves to 90 nanometer to 45, the error shouldn't be too big. We compared the area and delay metrics. However, we don't compare power. There's two major reasons. One is that power data is actually very difficult to find, and the testing conditions are never standardized, for example, test vectors and how you measure it and so on. It's also a little bit less important for FPGA processors because as an FPGA user, we're basically spared from not melting the chip. So here's our first set of results. This is a comparison of FPGA versus custom CMOS processor cores. So we looked at two processors from Sun, the Spark T1 and T2, and cited from literature two processors from Intel, the Atom and Nail. This comparison compares just the processor cores. It doesn't include the large L2 or L3 caches. And we compare them to the area of a custom processor calculated from die focus, as this sort of demonstrates. The FPGA implementations used RTL that is slightly optimized from the custom implementation. The Sun processors come from the OpenSpark project, and the Intel processors come from their work. So we didn't synthesize the Intel processors. So here's the area comparison for our four processors. We see that there's an average of around 23x area. That means that the processor core occupies 23 times the area on an FPGA than on the original custom processor. And we see that out of the 4 processors, the variation isn't actually too big between the 17 and 27x. And even the really complex Nehalem processor, the area ratio isn't particularly high. Here's the same results for speed. We have an average of around 22x. We don't have a number for Nehalem because they time multiplexed the interconnect and ended up with 500 kilohertz. So out of the 3 processors, the average is 22x. So here we get to the second part of our results. In the second part, we do the same comparisons to a set of building block circuits. And then we compare the results to the overall area and delay for processors to see which blocks are better and which blocks are relatively worse. Due to time constraints, we're only going to go through one example on SRAMs. So we start with single-ported memory arrays. Okay, so data for the custom version of memory arrays come from both literature, published design examples, and also from the cacti, area, and delay models, which is a model that is supposed to be relatively representative of custom SRAM. So we now have more data points. We compare both to an analytic model and actual examples. On the Stratix 3 FPGA, there are 4 ways you can build memories. There are 3 different hard memory block types. And as always, you can always build any circuit using registers and muxes. In this section, we're going to look at memories with 32-bit wide ports to limit our space. Here's a plot of our density, which is roughly area. Here's a plot of bit density of an SRAM versus the size of the memory array. We see at the top here, these 2 series are for cacti and custom design examples. We see that they correspond fairly well. At the bottom here, we have our 4 types of FPGA memories. So the gap here is the ratio, the density ratio between custom and FPGA RAMs, and you can see that the gap between custom RAMs and the best FPGA RAM is roughly 2 to 5x. This is actually fairly good compared to the overall area ratio of 23x. We can also see that using registers and muxes to implement RAMs or to store anything is very inefficient by roughly 2 orders of magnitude. So hard FPGA RAMs are a very good thing. Here we have the same plot, except it's Fmax of the SRAM versus the array size. We see the same trends. Custom is faster than FPGA. In this case, the delay ratio is a little bit greater at 7 to 10x. However, it's still better than an overall delay ratio of about 22x. For really big arrays, on the FPGA, we have to stitch together multiple hard blocks together, which adds delay. We could, in theory, pipeline that out. So we didn't do that here, so it's not really a fair comparison. So for the smaller RAMs, we have 7 to 10x. When we move to multi-ported RAMs, things start getting bad. Okay, so here we show a very similar plot of bit density versus the number of write ports. We chose here to use a 2 kilobit memory with twice as many read ports as write ports, because this is what you might find implemented in a register file, which is a consumer of these multi-ported RAMs. So for this particular size, we're going to scale the number of write ports. The number of read ports is twice that. Okay, so for 1 write port, 2 read ports, we can replicate hard block RAMs to get more read ports. And for 2 read, 1 write, we have a density ratio of 7x. It's worse than the single ported density ratio, but it's not too bad. It's still better than our average 23x. However, as soon as you move to 2 write ports, you cannot use replicated hard RAMs anymore. So if you use registers and muxes to implement this, the density ratio grows to 143x. It's very inefficient. So There's an alternative method of implementing this using live value tables, which is from Eric's work, where you still use hard FPGA RAMs to do storage, but you replicate it more times. And you have a separate structure called the live value table that indicates which copy of your hard RAM has the most recent data. This closes the gap quite a bit, but it's still 23x, which is still quite a bit worse than with one write port at 7x. And it's quite a bit worse from 2 to 5x for single ported memory. So our conclusion is that multi-write ports is worse than one write port, which is worse than single port. The Fmax ratios are far less interesting to us. We don't know them. It's about 9 to 15x for the entire range of ports. So here's a summary of all of our comparisons, including those that we didn't cover. So as a reminder, our average area is 23x, our average delay is 22x. You can see from here that the area ratios tend to vary quite a bit more than the delay ratios. We saw that single-ported SRAMs are particularly efficient on FPGAs. 2 to 5x is much smaller than 23. We saw that multi-ported SRAMs are significantly worse than that. We also saw that CAMs and multiplexers are particularly area inefficient. Blocks that have structures that have FPGA hard block support, like multipliers and adders, have a fairly good area ratio, which is quite a bit below 23, except that the delay ratio actually is fairly average. So the hard blocks contribute more to an area savings than to lower delay. We also observed that the delay of a pipeline latch is actually a little bit lower on FPGAs relatively than on custom. And this has an impact on the gains from pipelining circuits. So a shorter delay will encourage longer pipelines. And all of these costs will have an effect on your microarchitecture choices. So how? So here's our third part. Shown here is a somewhat abstract version of a out-of-order processor pipeline. You can see that most of the processor is in order, except for this execution core here that's out of order. The out-of-order part actually, the design of that actually varies quite a bit between different designs. The in-order part is fairly standard. So in this section, I'm going to go through just a few examples of how you might change microarchitecture to mitigate expensive multi-ported RAMs, that show up here, expensive CAMs, and also expensive multiplexers. First, expensive multi-ported RAMs. We saw in an earlier section that multi-ported RAMs are expensive, but multi-write ports are even more expensive, so we want to avoid that. One way to do that is when you build a multi-issue machine, you could choose to cluster your register files. Before, we had 4 read ports, 2 write ports for 2-issue machine. If you break that up into 2 clusters, you could build a machine that only has 1 write port, even though you still keep multiple read ports. This is preferred because it is less inefficient than multiple write ports. Our second example is for CAMs. So out-of-order processors usually use a CAM for their instruction scheduler. However, some processors also use what's called the reservation station that, in addition to scheduling, also stores the values of operands. That makes CAMs bigger than they really have to be. Here's an example from the Intel Pentium Pro, which was actually used up until the Halo. You see that operand values are stored in 3 places: the reorder buffer, the retired register file, and the reservation station. So that means that there are 2 multi-ported RAM structures here, and a CAM that stores data. AMD's version is slightly better. It still stores the operands in 3 locations, except that the reorder buffer now has fewer ports because they changed the register file. But it's roughly the same. Some processors have used what's called the physical register file organization, which only stores operands in the physical register file. The advantages of this is that there is only one multi-ported RAM. And also, the scheduler, which still has to be a CAM, no longer stores operands, which makes it much smaller. So we prefer this organization because it has fewer multi-ported RAMs, and it makes the CAM smaller. Our third example involves multiplexers. The bypass network of an out-of-order processor consumes quite a few multiplexers, and we want to try and reduce that by changing the microarchitecture. So in a typical core, we might have 2 bypass multiplexers per ALU because each ALU has 2 operands. Multi-issue machines just make this worse by making the multiplexers bigger, but you still have 2 multiplexers per operation. What we could do is look for chains of dependent operations and fuse them. So what we save here, we're still doing 2 operations. However, we save one of the bypass muxes because we're chaining a dependency using a point-to-point link instead of a bypass mux. This saves 1 bypass mux. Now we have 3 bypass multiplexers for 2 operations instead of 4 for 2 operations. A very common example of this is the fuse multiply add instruction. That works particularly well because the ALU is actually much more efficient than doing it separately. There are also many other proposals that can find chains of dependent operations and fuse them without changing the instruction set. And this is, I think, a promising area for future work. And we'll get a greater area performance gain on soft processors than the hard processors where these ideas originally came from. So in summary, we need to measure the cost of building block circuits in order to guide microarchitecture design choices. Simply knowing the overall difference between substrates isn't quite enough. We need to do this because the relative area cost between different types of building blocks vary by up to 2 orders of magnitude. So it does have a significant impact on microarchitecture. And we also saw a few examples of how the microarchitecture could be changed to mitigate the FPGA substrates' unique properties. So with all of these measurements, our next step is to use these measurements to guide the design of a larger and higher performance soft processor by leveraging the big body of existing processor architecture research. Thank you. Any questions, please?
Okay. Any questions?
In the case of the block RAMs, or the multi-port RAMs, you said that write ports were much more expensive. And I think that's mostly because of limitations of the block RAMs on the FPGA. So would you say there's an argument to making hard RAMs on the FPGA that have more write ports built into them?
No, because what you put on an FPGA depends on how often those things are used. Multi-write programs are very rarely used. Like even on a processor, basically everything except the register file we could kind of reorganize so it doesn't require multi-write ports. And even the register file, I just showed an example that you could even tinker with that to not need it. So it's probably, from an FPGA designer's point of view, it's probably not beneficial. It'll benefit a very small subset of users.
Well, if you can make the argument that any large system-on-chip FPGA probably has 1 or 2 small embedded cores on it, then presumably most users would use a small number of these multi-ported RAMs to some benefit.
Well, if you can design around it,
yeah,
then you probably don't need it. If you remember another cost of it is, if you recall the single-ported SRAM graph, there was a 2 to 5x gap between custom and FPGA. And actually about half of this gap is because the FPGAs actually chose to use dual-ported memories, when in most cases you only needed single-ported. So they are already paying a price for having dual ports. If you're saying, let's go to 4 ports or 3 ports, that price will actually increase for the majority of designs.
okay.
So in the case where you're splitting the multi-ported register file, if you could bring up that slide. Yes, that. So now this means, however, that does this mean that the compiler now has to be aware of the structure and have to deal with it?
Actually, no.
No?
You could just say, I'm going to fetch groups of 2 instructions. The first one goes into the left half, the second one goes to the right half. And you will suffer a little bit of performance loss, because there are certain cases where this half might be empty, this half might have instructions ready, but you can't take 2 instructions from here and execute them. So there's some IPC loss, but you don't actually have to change the compiler. In fact, I believe AMD's processors all do this right now. They actually have separated schedulers.
All right.
Do you have any back of the envelope estimates on how much savings you could get from these improvements?
As an overall system, no. I could say for this one, you go from 143x down to 7. I don't know.
Actually, another one. So when you put that list of speed and error comparisons, muxes has stood out as, you know, they're delayed 20 to 75, whatever, but why are they so big?
I actually don't know. I think my best guess at the answer would be they are actually very tiny and custom. You could build tiny muxes using a single transistor, maybe 2 transistors, whereas a single LUT would be at least several hundred transistors.
Okay. Yeah.
You should show your comparison.
That's on the other slide there.
So, just curious, how did you actually get the data? Because usually Intel publishes overall data. How would you actually down to the mux level delay?
The mux estimate actually doesn't come from Intel. The mux delay is very weird. I don't know if I should explain this.
Try it.
I will try and explain this. So,
Do you have the slide there?
I have it in, did you download my other slide?
The long one?
It doesn't matter. I will try anyway.
Okay.
Okay, so FPGAs are made up of, in the static stream, it's made up of ALMs. ALMs are basically a bunch of lookup tables to chain together user access. So, assumption number 1, the ALM's area is mostly muxes. I don't think that's true, but let's go with that assumption for now. Okay, so if we build, so the way we measure area is we build the FPGA circuit, then we compare it to the custom, and we take the ratio of the areas. So we're going to build an ALM, code it in HDL, synthesize it, and you come up with the FPGA equivalent, which uses a bunch of ALMs. And we say the number of ALMs used to implement an ALM is the area ratio for an ALM, and that ratio is 52x. So that's a lower bound for what's the area ratio of a multiplexer. The number 1, we only implemented just the multiplexers in the ALM. We didn't implement the configuration RAM, the routing, and so on. So 52x is a very, very lower bound. And then we're going to say, well, the global routing occupies at least 50% of the chip. We also ignored all of this configuration RAM and so on. The lower bound is at least 2x below. So I just put greater than 100x. I don't have a good bound, but I'm pretty sure 100x is lower than the actual number.
So another question here is that I think the previous study by Professor Rose shows that the delay ratio between FPGA and ASIC is usually like 2 to 3x, if I remember correctly. Much lower than the area, right?
Yeah, 3 to 4.
3 to 4, yeah. So now this study that you have is actually a much larger number. So I'm wondering what explains it. Is it because you are really comparing with custom design instead of ASIC methodology, or some other reason?
I don't have numbers for this, but my belief is that it is a big part is due to custom versus ASIC. And that custom is highly delay optimized, even if the area is higher. So if you actually compare it to that work, the area ratios that we got here are actually pretty similar to ASIC versus FPGA, even though you would expect custom would have much denser logic. So the area ratio is about the same, but the delay ratios are a lot higher for custom. I can also cite Kreutzer and Schinner, where they compared custom versus ASIC processors and ended up with 3 to 8x delay between standard cell and custom. So I think that's where the difference comes from.
Now you're talking about putting rather complicated and larger soft processors on FPGA. There's been a number of chips released with hard processor cores in them, built in. And what I'm what I would like to know is, can you discuss or comment how these larger cores, right? Because you're talking about adapting architecture to a standard FPGA substrate, right? Instead of adapting the FPGA substrate to more of the application side, right? Can you comment on how this can be used in the future, right? So when you can actually put these, and you're going to use these cores as the center of activity, right? Never mind the smaller kind of NEOs or microblades soft cores, right? You want to put in complicated cores on the chip, right? So can you comment how this can be used in the applications where you will be taking up a large portion of an FPGA, but you're gearing the architecture to the substrate? I'm just trying to see if you've done a comparison perhaps with the hardcore processors on FPGAs and what kind of a delay versus those your architectures would incur.
So I haven't looked at the hard FPGA processors, although I would assume this comparison roughly extrapolates to that, and I would assume that the hard processor on the FPGA would be far more efficient than a soft processor. Having said that, historically, there have actually been hard processors on FPGAs even a decade ago, but soft processors are basically still useful for certain tasks when they're fast enough and small enough. So even though they have been putting hard processors, they haven't actually managed to take over all of the soft processor market. So I think as time goes on, we will still see a certain threshold at which soft processors are useful for the slower and smaller tasks, and hard processors are useful for the bigger and faster tasks. But I think performance will continue to improve for both. Meaning, soft processors will get faster, hard processors will get faster. The boundary between whether it makes sense to use a soft processor will also increase over time because the cost of the soft processor is constantly reducing. If you look back from 10 years ago, a soft processor took up 5% of the FPGA. Right now, the same processor, soft processors, which haven't really gotten much bigger, are taking up 0.2% of the FPGA. And perhaps we could afford 5%. And that would give you a much faster soft processor.
Right. The issue I'm grappling with is that the soft processors available today are rather small, right? So you can have 100 of them in a chip, and that's a good architecture to have if you have lots of parallel computation to do or whatever, right? But the processors that you're talking about implementing are large, like these would be taking up a chip.
No,
or
they are larger, but I am really only targeting 5% instead of 0.2%. So I could probably fit, I don't know, let's say 10 of them on a chip instead of
so that would be more of a Spark and perhaps Atom.
Those are actually much bigger than that.
Right.
So the sizes of processors actually span several orders of magnitude. And these Spark processors that I compared actually do take up a whole chip, and the Halo takes up like 4 chips. So I'm not targeting that, but I am going in that direction, and I am saying that we should move past NEOS, although certainly not to this extent.
So perhaps you can say that your results here for the delay in the area, once you do implement architectural changes, will be different.
Right. I do expect them to be lower once you specialize in microarchitecture. These numbers apply for microarchitectures that target custom resynthesized.
Thank you.
Okay, I guess we should